Our next speaker is online, is right here. He is based in the University of Massachusetts Amherst. He is Talha Mebu, and he has been examining, I assume, a number of things, but what really caught my attention was his work in examining the carbon footprint in the context of federated learning. It's something that I personally have done a bit of work on in the past, along with some other collaborators. And so I'm always curious about how things have been moving on. Um, yeah, thank you for joining us today. It's fantastic to have you here, and I'm really interested to hear your talk today.
Thank you so much. I hope you can all hear me. Uh, all right. Can you all see my slides?
Yes.
Okay, perfect. First of all, thank you so much, Nick and Flower Labs, to have me here. It's a pleasure. My name is Talha, everybody. I'm a PhD candidate at University of Massachusetts Amherst. And today, the work that I will be presenting, as Nick mentioned, is basically how we can optimize for the carbon footprint of federated learning. This work is still under review, but the authors, besides me, that worked on this paper are Noman, Jesus, Mike, and David. This is a joint collaboration between MIT, Telefonica Research, and UMass Amherst. A little about myself. Obviously, I work at UMass at the Sustainable Computing Lab, and we mainly work on like designing sustainable or energy efficient solutions in like data centers, edge computing, cloud computing, and my research focuses also towards like how we can make the computing, like specifically machine learning, more sustainable and more efficient. With that, I think I would start my presentation. And the big question, obviously, is like, why is this problem even important? Like, why do we even require to like make the federated learning more carbon aware? And the answer is basically, I think Nick mentioned photon. I've read that paper like a lot of times, honestly. And that paper, and along with like some other studies that we can see here, is shows that we're running into the problem of like having confined data at one location. And in order to have access to more public data, we obviously have to go public. And then that essentially means a more collaborative, distributed environment for training. And what's better than federated learning to do that? So as we see from this graph, we show that by 2028, if we keep training the LLMs model as we are right now, we will probably run into the problem where we don't have enough data in private settings, and we need to access the more global, more public data. And federated learning, while preserving the privacy of the data, is the best fit to do that. However, existing techniques generally focus more towards how we can like increase the performance of the federated learning or machine learning models. They generally overlook, or they ignore the fact that there's a big carbon footprint associated with that training, as the energy that we use in order to train those federated learning models generally come from the uh, electric grid, which operates on like coal or gas or like those non-renewable resources. So this graph actually shows the comparison between uh, uh, the carbon footprint of centralized versus the federated learning settings, and we can clearly see the difference that at certain locations, the carbon footprint is way higher compared to the centralized. So there's a need that in federated learning, there's that given its importance to like train foundational models in the future, and its increased significantly larger footprint compared to the centralized, there's a research gap that we need to make this federated learning more carbon aware and reduce the carbon footprint while maintaining the performance, so that we can make the training more sustainable. And that is basically where our system comes in. We build this system, which is a joint optimization for the carbon efficiency, the model accuracy, and the training time. And essentially, we are navigating this trade-off, which is a three-way trade-off between the carbon efficiency, the model accuracy, and the training time. Okay, so before I actually talk about how we actually implement stuff, how we use Flower or the design of our experiment, I really want to focus on this very important point, how the carbon varies over time, because as I was listening, like you mentioned, Nick, that what is the idea behind the project? How did we actually come up with the intuition for this project? And the idea was basically like we looked at the energy sources, we looked at the carbon intensity, which is essentially the how much carbon is being generated when a certain device using 1 kilowatt hour of energy to perform certain task or computation. And from this global carbon intensity graph, we can see the dark brown areas are basically the ones where the energy that is being generated uses either coal, gas, or like those non-renewable resources, so that the carbon intensity is higher compared to some of the greener regions, which uses, for instance, France uses the nuclear energy to nuclear sources in order to generate electricity, and hence uh, the carbon intensity in those regions is smaller. And the idea is basically that if the carbon varies over time and across space, we could potentially use this spatial variations or these temporal variations in our advantage while we're making the selection in the federated learning. So that was our basic idea, or like the basis of like where we started. If you look at the left bottom graph, this shows the carbon intensities for three different locations across the globe for 3 different days, and we can see that uh, the carbon actually varies significantly between the two regions at the same time, and also the carbon varies significantly for the same location at different times. And that variation can be up to 30 times difference in spatial variations, and up to like 6 times variation in the temporal variations. Uh, and that basically was the major motivation behind using these carbon variations in order to optimize for the carbon footprint of the federated learning, given the nature of federated learning being so uh, distributed, that we can actually opt to go for a more distributed environment. Okay, so here I present the actual design or the solution of EcoLearn. So I think it's very clear now that how do we make the selection of the clients is based on the carbon emissions. However, we can't just solely make the selection based on carbon, because uh, it is very likely that always the low carbon clients would have lower utility. Now, utility is like a known concept in the literature, which essentially tells us like how important a certain client is. So we need to make sure that we're selecting clients which not only reduces the carbon, but also enhances the performance of the training. So the first module that we look into is the client selection, which actually selects clients based on their more utility and less carbon. Um, the second fact actually comes the second module comes from the fact that since the carbon varies and the utility of client is actually larger, or is greater in the initial phase than in the later part of the training, we can basically scale the number of clients during the training process. So we don't really have to train on same number of clients throughout the whole process. We can scale our idea is that we can scale more during the initial phase, which is basically called the critical learning period, and then basically dies down. The number of clients that we select dies down eventually, because there marginal increase in the accuracy. And doing that, not only we enhance the performance by selecting more high utility clients in the beginning, we also reduce the overall carbon footprint, because the average number of clients that we select over the training period reduces, because we lower the number of clients at the end phase of the training. And the third basically is to eliminate the factors that impact the performance in a negative way, and that is the stragglers. Uh, Boyu also mentioned in his presentation that how stragglers overall elongate the process, especially in the synchronous aggregation, that we are always waiting in the heterogeneous system. We're always waiting for the slowest client. So in order to avoid those stragglers, in the past, people have been using the over provisioning factor, which is like we over provision clients by a factor of, let's say, 30%, and then we wait for the first, let's say, n number of clients to respond, and that we're hoping that we're avoiding the stragglers by doing so. We saw an opportunity there. Again, the carbon variations. We saw that what if we increase the number of over provisioning during the low phase carbon period, and then reduce the number of clients that we over provision during the high carbon period. And that essentially makes our system even more carbon aware. So we introduce essentially in EcoLearn, but we introduce the carbon awareness in the client selection. We introduce the carbon awareness into client scaling and the straggler mitigation techniques. And essentially, that helps us to increase the performance or maintain the performance while significantly reducing the carbon footprint of the FL. Okay. So this is the system design that we're using. Obviously, I think the major thing that I want to talk about is how we use Flower framework in our system, given I'm presenting at Flower Monthly. So I think as I have discussed, we have three major modules. How can we select clients? How can we scale clients? And how can we over provision? We require obviously the carbon intensity information in order to do that, associated with each client or location. As a matter of fact, we need to define some of the configurations. I'm pretty sure you're familiar with like how we can configure the federated learning settings in a certain way. And the most important thing is how we can use the utility information in the global aggregator, along with the accuracy of the model, in order to allocate the critical learning period within the server. So the way it works is that we define our own custom criterias based on like which specific clients do we need to select. That basically tells that information into the client manager, which samples those clients, give that information to the configurator in the averaging, the configure fit, as people are familiar with that, which basically configures the very specific client for the next round of the training based on the utility, carbon, and the fact that if certain clients have already been selected before or not. And all of this information is being kept at the server in the Flower framework, the aggregator. And essentially, the server returns the list of the clients that needs to be selected in the next round of the training. And doing so repeatedly over rounds of training, we overall reduce the carbon footprint while we're trying to maintain the accuracy of the model. For the evaluation results, I will go through them quickly. I believe the major result that we have is that we reduce the carbon footprint by a factor of 11 to 14% for different levels of non-IAD or different levels of distributions of data. And I think the major carbon savings that we see is for like the extreme non-IAD settings. And that is like you can see the carbon agnostic approaches are using significantly more or emitting significantly more carbon compared to the carbon aware techniques, which is one of them is EcoLearn and its sister policies. We reduce the overall carbon footprint significantly while we maintain the accuracy as seen in the graph on the left. Which takes me to the last point, which is we rely on the Pareto frontier, which essentially means that we optimize or we efficiently optimize the carbon compared to the accuracy, compared to all the other baseline policies. So it's like if you just select clients based on the utility, yes, you will have better accuracy, but your carbon would be bad. If you're just randomly selecting clients, you probably would not have good accuracy or carbon. As a matter of fact, just selecting clients based on the carbon is not good either, because then you will be getting to your model will get introduce bias in the system and will affect the performance. So the best way is to basically go moderate and like select both of these metrics into the consideration while selecting the clients. So as you can see, EcoLearn basically efficiently optimizes both of these or navigates this trade-off between accuracy and the carbon efficiency. And yeah, with that, I would like to thank all of you who are listening. If you have any questions, you can or want to read this paper, look into the actual results or methodology, you can go on my website. The paper is linked there. Or if you have any question, my email is also attached here. So you can, if you have any question you want to contact me, you can do that. And with that, I would like to thank Flower Labs, Nick, again for inviting me here for an opportunity to give the talk and the collaborators for their contributions and their work.
Great, thank you so much. Wonderful stuff. So just the same as we ran earlier, if anyone who's part of the Zoom webinar, you can raise your hand. I'll unmute you. You can ask a question. I'll browse around some of the other channels to see if people paste their questions in there. Um, yeah, so feel free if anyone, this is a good opportunity to ask questions about this work. Don't see anything coming up yet. Um, I guess I'll ask a question, and that was back on slide 8. You had different baselines, and so I'm sure you mentioned this, but so random is random client selection under like Fed average or something, I suppose.
Yes, that's true.
Let's see. And did you have any evaluation where it would kind of correspond to the carbon emitted under a maybe some uh, I guess a selection policy that is based on where the data happens to be. I guess it'd be somewhat of a simulation, right? Data might be in 7 hospitals, and so you could imagine the data spread under that sort of regime, and then you could assign carbon maybe to actually real hospitals, and then see what it would be like. Because it's not that wouldn't be random. You'd be training a model based on, well, it depends on what the type of selection criteria is, but you probably would be doing it. Maybe equal, or there's different things that happen in a real federated system. So I wonder if you have a sense between an actual operating system and the carbon of that system, and maybe random in your one to see the gain.
Well, I didn't really quite catch the last part. If you could repeat that, please.
Oh, sure. I was just thinking under us. I mean, cross device, often
Mhm.
clients are selected at random, but
Right.
I guess under cross silo, you often have a specific. You might move between the clients, but it's quite deterministic or prescriptive. And so, do you have a sense of like in that type of setting, what the carbon gains might be?
Right. I think for the baselines here, uh, for the random, we just thought, like how if the server has access to 100 clients, how we can just randomly select, like, let's say 30 out of those and just look at the carbon emissions of those. And as far as like the intelligent, I think one of the major concept of this paper was also to show that having these intelligent client selection policies can actually help and not degrade the performance, because there's this general notion in the community that having this intelligent client selection policies introduce bias, because we're generally looking into like specific clients because we want to reduce the carbon or cost, as a matter of fact, like any other metrics of cost. So doing this, we also show that we can have arbitrary notion of cost. In our case, that is carbon cost, for instance, but this could also be battery consumption or like energy, or like as a, it's like an arbitrary cost metric. So I don't really understand exactly the like or I can't answer like what would be the sense of like different criterias here, but I'm pretty sure like using some intelligent client selection, we could take it further, like a notch further. We can overall reduce the carbon emissions further if we look into other metrics.
Yeah, perhaps my question was ill-formed. I was just sort of thinking on the fly what would happen under a cross silo setting. Um, But but anyway, just thinking about it, and most of the cross-device settings,
Hmm.
you have training runs that last for weeks, as Google and
Right,
other folks have shown, and
right,
so you probably can, when you interact with certain devices, get the same model, but for vastly different carbon footprints, assuming there is variation in your population, which there probably should be.
right,
Um,
right.
yeah, cool.
When you say
Um,
cross device, you assuming that those devices are kind of co-located in a similar region, so there are less variations?
Oh, I don't know. I haven't really thought about this as much in a practice. I mean, I guess it depends on how big your population is and how much flexibility you have to interact with each one and still arrive at the same model.
Hmm.
But on a certainly these large scale cross device scenarios, you would imagine that flexibility does exist.
Hmm.
Um, so that's interesting. Um, I'm rambling on here, but we do actually have another question that I can read out. And so the question is. Uh, do you assume clients use different compute resource? And are you selecting also based on the client's energy consumption? So that those are two questions. Do you assume clients use different compute resources? Uh, what
Right.
would you say?
So, uh, in our in our system, obviously we have this heterogeneity in terms of data, which we're assuming that, there are different data distributions. We do not have experimental results or evaluation results on like different types of GPUs or like the heterogeneity in terms of the system that we're using. However, we're positive that we can certainly, evaluate this system on like different types of like GPUs or hardware, as a matter of fact. For the second part, which is the energy consumption of the device. So in this regime, there are a couple things. One is like the energy's carbon efficiency, and the other is the energy's carbon intensity. So we essentially want to make sure that uh, the computation's carbon intensity, which is essentially like how much carbon dioxide are we generating per cycle of computation that we are performing, and that is a factor of like how much computation that we're performing per cycle given the kilowatt hour of energy that we're using, and basically the carbon dioxide that we generate given the kilowatt hour of energy. So the point here is that in this evaluation we do not look into the actual energy consumption of the specific devices, but we assume that given this carbon intensity, which is kind of like the inverse of the carbon efficiency, we're capturing that essence. So like if a certain device, obviously there's an assumption that we're using 1 kilowatt hour of energy on that specific device. If that changes, would that affect overall our results? The answer is no, but that would change the overall value of the carbon intensity, but the metric still remains the same. So I think we have looked into like if we need to add that discussion. We have that discussion in the paper, by the way. So if you want to go read, like we have this discussion in the paper. But do we want to evaluate our results with like varying energy consumptions? We realized that that would not overall affect the final results.
I see. Cool. Yeah, well, and this is one of these issues that there's a lot of depth to issues like this because it sort of expand outside of um outside of computer science, to be honest, and starts looking at things like where does energy get generated and all the other secondary things that are quite critical. Um, awesome. Well, I'm glad you're really working on this because I think it's really important. So thank you so much for joining us today.